So first of all, I think let's move on to our hands-on session. So everyone please move to 5 use chunking. Again, inside day 1, hands-on number 5. And let's just think it through. What do we need to do if we want our domain to first be decomposed into different chunks, and then we want to hand each chunk to a block? So what will change in our code? Well, first of all, for sure, we will need to define a chunk size that we like. Then we need to also change the work division, because now we know exactly how many blocks we have or how many chunks we have. And according to these number of chunks, we launch a certain number of blocks. Also, we now, since have a fixed number of elements that each block processes, we can know how many threads per block we need. So obviously, this is something that we can explicitly tell Alpaca to do. And once you update the work division, the final thing that we need to do is actually go inside the kernel code and make sure that our kernel for every block processes the whole chunk. And over here, we got some questions yesterday about, what happens if I have more elements than I have threads. And so these are the things that can be handled inside the kernel now. Because say if you have a huge chunk size, which is much, much more than the number of threads you have, you've already split the problem up into different blocks according to your own problem parallelization scheme. And inside the block, you can just ask the threads to work on in parallel all the elements. And then if there are elements left over, keep repeating inside, for example, a for loop that, hey, do work. And if there's some more work remaining, do that as well. So all the threads will keep on doing work until it is finished. And that is the central idea of how you can use chunking. So let's start with it. And let's go to our CPP file and first decompose our domain. So how do we do this? We know that we had a domain of 64 by 64 blocks, nodes. What would be a good size? Can anyone in the audience suggest a reasonable size for our chunks? My total problem domain is roughly 64 by 64 plus a couple of cells above and to the sides. But we don't care about those. I just want to decompose my central domain. 8 by 8. 8 by 8 is a very good suggestion. So let's start by doing that. Let's define our chunk size. So you can go to line 108. Over here, we have some instructions. So it says we need to define an appropriate chunk size. And we can have of course, it is an alpaca vector. And we use 8 by 8. So what led to you choosing 8 by 8 for a chunk size?
Nice bicycle, like which most accelerated buttons are, and also our domain size is to this.
So the answer I got from the room is that we use 8 by 8 because it is nicely divisible by 2, which is what most accelerators tend to prefer. So if you have a GPU, you probably have, say, 64 or 128 threads in a block, maybe. Things which are nicely divisible by 2 usually are nice to use in computer science. And the second comment was it is also nicely dividing our domain, which is 64 by 64. And this is kind of important. If, for example, you had a chunk size of 10 by 10, this would mean that you have 6 blocks which are completely full, and in the 7th block, you need special handling to make sure that your threads are not working on data which does not exist. And if you choose a chunk size which is nicely dividing your domain, you don't have to have these extra checks. And this is important. If you want to write really high performance code which runs fast, you want to avoid having extra checks inside your kernel. An extra if condition really slows down your performance. So when you're manually deciding how to parallelize something, this is something you need to take care of. So I will define my chunk size. What next? I need to split the domain into chunks, so I need to figure out how many chunks I have actually. So to do that, what do we do? How do I find out how many chunks I have? Yes, Brian.
Just define the total extent of range by the chunk size.
Absolutely. So we divide the total number of nodes we have by our chunk size. Again, it's an alpaca vector. And we divide num nodes by chunk size.
Doesn't it do that? Isn't that overloaded in the vector?
So the question I got was, do I really need to do num node 0 divided by chunk size 0? And can't I just directly say num nodes divided by chunk size? Sadly, not yet. Yes. So now I have the number of chunks I have. Since I chose a nicely divisible chunk size, we don't have to worry about integer division and having remainders. Finally, I want to create a work division for this. So how do I do this? Well, I already know how many blocks I want. The next question is, how many threads do I want in a block? Well, this is easy. I want as many threads as there are elements in my chunk. So if my chunk is 8 by 8, that means 64 elements. I only want 64 threads. This is easy. But for example, if my chunk size was something larger, say 16 by 16, I would need 256. And this is all well and good, but maybe your accelerator does not have these many threads to work on. Maybe you are on a CPU and each block only has one thread. Or maybe you're on an older GPU with a smaller number of threads per block. So when you're trying to explicitly tell Alpaca how many threads you need in a block, you also need the maximum limit of what your hardware can support. And to get this, Alpaca provides something we call function attributes for the kernel. And we can basically ask Alpaca for things like this. So how many threads can you run in a block, for example? So I will show you how we can get this, and it's really easy. It's Alpaca get function attributes. And this is how you can ask Alpaca for all of these details. So I will call it kernel function attributes. And what it needs is your device and your kernel. So my kernel is the stencil kernel. And of course, like everything else, there is some code duplication over here for performance reasons. And this is how you can get the kernel function attributes. And this is what you use to query, hey, how many threads can I really use? And you can ask it for max threads per block, for example. If you open the documentation for function attributes, you will find some other useful things, and I recommend that you do it. For now, we only need max threads per block. So, okay, I know how many chunks I have. I know, therefore, how many blocks I want to launch. I know how many threads I want in a block. Can someone tell me how many threads, how can I calculate the exact number of threads I should tell Alpaca to launch in a block? So I'll help you out a little bit. My chunk size is 8 by 8. So each block needs to deal with how many elements? Come on. Okay, 64. So each block is dealing with 64 elements, but I'm not sure if I have those many threads. So what I do is simply say that my threads per block should be the maximum of either max threads per block or the product of the chunk size. So we can do this a number of ways. For example, we can say if my max threads per block is less than my chunk size dot prod, so the product of the chunk size, then I need the maximum number of threads, because what you really want to do is utilize your hardware to its maximum. So use all the threads you can get, and if they're more than enough, use exactly as you need, as many as you need. And
Can we not use STD?
so the question is, can we not use std min? I am not 100% sure if we can, because what we are dealing with is alpaca vectors, and I'm not sure if they follow the interface required. Yes, Richard. So this line is currently incorrect. And the reason for this is eventually what I want is the number of threads in a block. And I want to pass this to the work division. And what the work division requires is an alpaca vector, and it will be a 2D vector. So it would say how many threads you want in the x direction, how many threads you want in the y direction. And currently, this is, for example, dealing with scalars. So this is a scalar number, this is a scalar number. So what I really need is to say, okay, I need an alpaca vec. Of, for example, max threads per block, comma 1. So this will create basically a 1D array of, or you can do it the other way. So this is how many threads you will launch in every block. And finally, the next step is to create the work division. Earlier, we were letting Alpaca do it for us. We defined a kernel config, and then we said get valid work div. I will remove that in a second. The way you can do this now is by saying alpaca work div members. So this is the interface we use when we are manually defining our work division. And say, since this is only going over the core, work div core, the same name as we had before. Can simply and num chunks. So really how many blocks you want. After that, how many threads you want in a block. And finally, how many elements you want in a thread. And I would like to pause over here and really think about what we're saying. This is really all a work division is. It tells you how we are dividing our problem and how we are mapping it onto our hardware. The number of blocks, the number of threads in a block, and how many elements each thread is taking care of. It's as simple as that. And everything we did yesterday also does this in the background, only automatically for you. This is how you do it if you have everything defined manually. And I can remove my old work division now. So at this point, we have successfully split up our domain into chunks. We have successfully defined a work division. And what's next is to change our kernel to use this new work division. And we will do this after a short coffee break. So to everyone online, if you have questions, now is a good time to ask. And then we will pause for 15 minutes, grab some coffee, and then start again. Continue with using this new work division inside the kernel. Any questions?
I didn't get quite right why use this ternary operator for the chunk size of the product. And I get the idea that we need to find out a way to actually map the amount of threads that we have per block to the word division, but I didn't get quite right the expression. chunk size?
So this has to do with what you get from the kernel function attributes. It tells you how many threads the maximum is for your accelerator, for your kernel, and this number is just a simple scalar. It's not a alpaca 2D vector. It's not saying, oh, you can have a 32 by 32 maximum. It's really giving you the product, and this is why you need to compare it with a scalar. Basically, what was mentioned, if you could do a std min, that would be ideal. So what we would like to write is a standard min of this thing, a vector of max threads per block, and the chunk size. And that's all this is.
What we are doing here is actually limiting the threads per block with the chunk size. If
Yeah.
the chunk size is too small, then we are setting threads per block to chunk size.
Correct. So the comment is, what we're doing is we're limiting the number of threads per block by the chunk size. If we have too many threads in a block, we say, oh, I don't want to use all of them. I only need chunk size number of threads. But on the other hand, if the chunk size is too large, then we are limiting it by the number of threads you can use. And then inside the kernel, we will use all of those threads to go over the full chunk. Okay, thank you. Now, I would...
Could you please show the kernel again?
The kernel.
The stencil kernel?
So this is the stencil kernel. Currently,
Oh, you can't make it constantly. Is this the empty span in the curl buffer?
I think I can.
Because you removed it again.
Oh, this is the next example. So
Okay.
yes, so
Okay.
yes, this is an oversight from my side. Thank you for the person online who pointed it out. I am missing a const for the current buffer. So now we break, and we will restart at 10:25, so a 15-minute break for coffee. Welcome back, everyone. So, welcome back. We left off after successfully chunking our problem into a certain number of chunks and then creating a new work division which manually sets how many blocks we want, how many threads we want in a block, and so on. So this is our work div core. Now what we need to do is we need to update our kernel to use this new work division, and also this new way to think about how work is divided. So we go inside our stencil kernel, and now we need to change the behavior. Earlier, every thread was going in here, it was looking at what element it is mapped to, it was a one-to-one mapping, and it was just updating its own element. But now, I'm not sure. So inside the kernel, I'm not sure if my thread only has to do update one element. I'm not sure if the thread I have even actually has to do any work. Maybe the thread I launch is number, say, 78, and I only have 64 elements I want to update inside this. Or maybe I have a situation where I have a large chunk size and each thread has to update multiple elements. So how do we do this? What is a good way to approach this? So one way to think about it is, say I have a chunk and this chunk has 64 elements in our case. And let's start by assuming I have only 32 threads in a block. So I have 32 threads in a block, and I can ask them like, hey, thread, what is your index? And you can update the index, the element at the corresponding index. What do you do after that? You can say, okay, maybe what we do is, once you are finished updating the first 32 elements, you continue and fill in the next 32 elements as well. So what we are going to do is basically fill in if my thread has an index, say 5,5, it fills in element 5,5 and then jumps over the number of threads we have, so 32. It jumps over 32 elements, goes into what would be 5,5 plus 32, split into our 2D grid, and then we can update. We will check again if this position is inside our domain. If it is, we update it. So this is one of the ways we can think about it. Another possible way to do it would be to say, hey, I have 5,5, I know that I want to update 2 elements. You can do some division and make every thread update 2 elements consecutively. But this one is kind of harder to reason about. And I won't go into details of it, but when you start writing the kernel for something like this, you quickly realize that it is quite, it's more inefficient to do it that way. So, yes, Nana?
Here you draw the chunk. This is the chunk.
Yes?
Chunk.
Is not sharing that one so that the
This
video
is the whole domain. This is the chunk you mean actually, and this is your block. Here you defined.
Yes.
Okay, this is the block. And this block of threads not only going to update this part, we'll also update the other data in the chunk. We have how many chunks? Maybe 4 chunks or 8 chunks.
Okay.
Okay, I just wanted to clarify.
Yes. So as you see in this case, we have less threads and our chunk is larger. So we have to go over it twice. Say we have a different case where we have more threads than we have elements in our chunk. In that case, we don't have to do anything. What we were doing previously would still work. So this way is kind of flexible. And I can walk you through how we write something like this. So let me share my screen again. Earlier, what we said that give me the grid thread index, we moved it by the halo size, and then each thread was updating its own element. Now each thread, so in this example, each thread has 2 elements, and it is working on the first element and then jumping over to the next one, increasing its own position by the number of threads inside a block. So if this is 32 threads inside a block, I update my current position by 32 threads inside a block. And I keep doing this until my whole block is consumed. So really think about this. What is happening? I have an initial condition of my index. This is the index of my thread inside a block. This is my initial condition. What I'm doing is I will continue jumping over the number of threads in a block, so 32. So this is my increment, and I will do this until all the elements inside my chunk are finished. So what we have is an initial condition, an increment, and a check. What does this sound like? It's a for loop. Really, a for loop is an initial condition, an increment, and a check. And this is what we will write now. So I can do something like this. For, say, I equal to, equal to what? Equal to my index of the thread in the block. So I don't have that currently. Let's find it out. We already did this yesterday. I will briefly repeat it. So I want the thread index in the block. So this is the block thread index, and you can get it using get index, block threads, and you have the block thread index. Superb. So I have a 2D chunk, so I will need a 2D for loop. Currently, I will only write the outer loop, but I will follow it up with the inner loop just afterwards. So this is my initial condition. What's next in the for loop? I need to check against my final condition. And what is the final condition? Well, I need to make sure that the thread index in the block, so which is I, is less than my chunk size, because I only have as many elements as my chunk size. So I check if I is less than chunk size, and finally my increment, I need to jump over as many threads as I have in my block, and that is what I do. I just say I equal to number of threads in a block. How did we get this? I don't have this information, but we learned this yesterday already, and we can simply write auto block thread extent is alpaca get work division, get work div, and this can give you the number of threads in a block. But there's another way you can do this, and this is, since you have already calculated the chunk size on the host, you can pass it in directly as well. And this is what we will do now. We will directly use our chunk size, because we know this is how many. No, sorry. Apologies, ignore what I said. Get work div is the right way to do this. So get work division, alpaca, block threads, and ACC. So again, I look at where I am, my thread index. I say, oh, is my thread index still inside the chunk? Do I have to work? If I have to work, then I do it, and then I increment myself by the number of threads inside the block. And then I check again, hey, am I still inside? If I am, then do the work, otherwise move ahead. So as you can see, this is quite a nice way to write something like this. And it really is how you usually write programs for GPU. So let me update it, being careful to not make copy-paste errors. And this is my inner loop. So what's next? Now, I need to know where I am currently. Earlier, it was easy to find out. I was using my grid thread index and just saying, okay, this is my position, this is the value I need to update. Now I am dealing with i's and j's. So what is my current location? Well, first off, my current location inside the block is simply an alpaca vector of I and j. I will add this is my local index, you can call it, for example. This is my local index within the chunk. So now we have another question. What about our halo? So this was our 2D domain, the 64 by 64 domain, and our work division was also defined by only splitting up the core cells. But the buffers still have our boundaries, one cell in each direction. So what I still need to do is shift it by the halo size. Just like yesterday, we just make sure that our thread is in the correct position. Okay, this is very nice. I know where I am inside the block, inside the chunk, but where is my chunk? This is one possible chunk, but my chunk might also be here, here, or here. So what we need to do is offset our local position with the position of the origin of the block. Okay, how do we do this? Well, I can get the position of the block by the block index in the grid and then move it by the chunk size. So this is my full chunk size, this 8x8 block, and I shift it according to my block index. So this is 0, 0, this is 0, 1, and I can simply multiply the block index with the chunk size, and I will have the offset for the local position. So this is exactly what we will do now. I will say the starting index for the block, say block start idx, is equal to, well, I need the index of the block in the grid. So I'm going to modify this because this is something we had earlier. I don't need this anymore. So this is grid block index. And I'm going to get the index of my block inside the grid. And I want to offset it by the size of the chunk. So simply multiply it by the chunk size. And this gives me the block start index. So very nice, I have the local index. I can say the global index is simply the block start index plus my local index. And that is pretty much it. I have the position of the element I want to update, and I can simply update it. And I move all of my code inside the for loop. And that should do it. So really, just to go over it again, we look at our current position inside the block. We say, hey, if my current position inside the block is within the chunk size, I'm going to do the work. And I keep doing this work until all the work is finished. And at every step, I jump over all of the threads that have been working. So I do my own work, I see what the last thread has been doing, and I jump over the number of threads there are and onto the next element I need to work on. And then you check again if you're still inside and keep doing it. So this way you can handle arbitrary chunk sizes. Now, really think about this. Does this work for chunks which are huge? Does this work for chunks which are much smaller than the number of threads you have? And really it does, because say your block thread index was 500 and your chunk is only 20 elements, well, you won't even go inside the for loop. You will exit as soon as you check initially. Similarly, if you have a really large chunk size, well, you just keep doing work by incrementing by the number of threads you have. And this solution will work for arbitrary thread sizes, for arbitrary block sizes. So, yes.
Can I make a suggestion? Could you move the hello size into the clock start index and the calculation? It would make more sense.
Yes, so the comment was that we should probably move the halo size into the block start index. And that is completely valid and I think a reasonable way to think. Block start index, yes. So we say the initial point of our block is offset by the halo size, and then, yes, this should work.
Halo size is 1.
Yes, the halo size is 1, 1 comma 1. So go back to my terminal. Let's try to build this. So this is the most important thing I want you to learn from today. Really how you can use a manual work division and what it looks like inside your kernel. How to jump over elements and how to make sure you can parallelize however you want. So creating custom work divisions and writing kernels which can efficiently support this. So let's try to build it. We are using MDSpan, so please remember to set using MDSpan to fetch. Oh no, some computers. Let's see. No matching function call for constant stencil curl.
Function signature is not correct. I think we have this in the chat too, so you. Could you check the caller side if you guess the chunk size? Yeah, the chunk
I do not. So we forgot to update our code to pass in the chunk size that we just defined. So let's do it. Remember that since we have code duplication, we need to do this everywhere. Let's recheck where we need to do this. So we pass in the current and next buffers, then we pass the chunk size before passing in the halo size. So we update it inside the execution. We update it inside the kernel function attributes. We no longer have the get valid work div, so you don't update it over there. Instead, you do it over here. Still not. Interesting. This probably has to do with the constantness of my MD span. No? Get function attributes.
something with the function, so you need to check again your signature. Do you also update the init kernel? Is it also
Use of undeclared next buff. Sorry about this. I removed the U by mistake. Let's try again. Now it works. Let's see. So over here, you can now see that we have an auto-generated work division, which is applying our boundaries, which we worked on yesterday. You can see that it has 11,1 blocks. Each block has 6,66 threads, and each thread is dealing with one element. The manually defined work div is like this, much more beautiful. 8,8 blocks, 8,8 threads in every block, and one element, and we are still executing correctly.
Can you also print the chunk size?
So the comment is, can we also print the chunk size? Yes, let's do it.
Before going from
Backslash. So this is just to print out the chunk size so you can see it. So the chunk size is 8,8. So over here we can see what happened. My chunk size is 8,8, And the number of threads I can have in a block is actually much, much larger. You can see the automatically generated work division selected 6,66 threads. And we have artificially limited this to 8,8. Therefore, we have a bunch of threads in our SMs which are just idle. And this may not be the ideal chunk size, therefore. So defining a correct chunk size is something you need to think about. You need to think about what kind of hardware you're going to run on and what might be a reasonable chunk size for that. Another thing we can try to do is run this on a CPU. And I will just do that shortly. Sorry. CPU sequential. And what we will see is, after a while, since it takes some time to run on the CPU, that on the CPU you can only have one thread per block. And you see it over here, block thread extent is 1. But you still have only 8,8 blocks. Earlier, you had 66 by 66 blocks, so really now each thread will have to deal with multiple elements. This is where the for loop comes in. And it will really go over all of them. In each block, there is only one thread on the CPU, and this thread goes over all of the elements inside the chunk. There is only one which really goes over all of it. And as you can see, this works as you would want it. Again, I would like to stress that choosing a good chunk size, choosing a good way to decompose your domain is important. And very often this comes directly from your physical use case. And yes, that is pretty much it. Now you know how to manually make a work division and how to exploit it inside a kernel. Any more questions? If not, we can directly move ahead and look at some more optimizations.